Hello. In this video, we are going to calculate the partition function for one final model system. We are going to, in this video, look at how to calculate the partition function for a gas and how we can include the interactions directly when doing this calculation. Before getting on to that, let's first briefly review what we have learned about the ideal gas in my previous videos. In my video on the ideal gas, we learnt that if we exclude the interactions between particles that make up the gas, we can write the Hamiltonian for a gas of atoms as shown at the top of this slide. Essentially, in this formula, each of the atoms has an associated three-dimensional vector of momenta, and a kinetic energy as a result. The classical Hamiltonian is just the sum of all these individual atomic kinetic energies. The energy of a microstate thus has no dependence on where the atoms are in the box. We showed that when this expression is inserted into our expression for the canonical partition function, and when the associated mathematics is worked through, the partition function is given by the expression shown here. This expression is useful as we can extract many of the relevant thermodynamic properties of the gas by taking suitable derivatives of the partition function. For example, we can recover the equation of state for the ideal gas by taking the derivative of the logarithm of the partition function with respect to V, as shown here. Alternatively, we can calculate the average energy of the atoms in the gas by taking minus the derivative of the logarithm of the partition function with respect to beta. We thus find that the average energy of the ideal gas is equal to the expression shown here, and that as a consequence of this result, the constant volume heat capacity for the ideal gas does not depend on temperature. Now, in actuality, and as discussed in another of these videos, we observe deviations from these laws, because gases are in actuality not ideal. As was discussed in that video, there are three respects in which real gases differ from this ideal. First of all, the particles that make up the gases are atoms and molecules with a complex internal structure, which often needs to be incorporated in the Hamiltonian. Second, there are interactions between these atoms and molecules. And thirdly, these atoms and molecules behave as quantum particles, so we should not treat them classically. In this video, we are going to learn to address the issue of the weak interactions between the particles of the gas. Thus, in terms of our now familiar matrix of model systems, we are going to be operating here. We are going to be looking at a system of indistinguishable and interacting particles. For the purposes of this video, we are going to suppose that there are no quantum effects to consider and that the particles do not have an internal structure. This is obviously not true in practice, but if we were to include all these features in a single model, it would quickly become unworkable. An interesting consequence of this is that when we use models like the one here, that is to say, when we use a model like this to fit experimental data, we will often end up incorporating numerical deviations from ideality that arise because of the internal structure of particles in parameters that describe the interaction terms, as there is no way within the model, or any theoretical model for that matter, to separate out components due to these three separate effects in measured data. This is one reason why computer simulation is so popular in this field. In simulations, we can neglect quantum effects and effects due to internal structure of molecules, and thus determine the effect of incorporating interactions between particles precisely. Without further ado then, let's now introduce the Hamiltonian that is going to be the subject of this video. It looks something like the following. You will notice that we have the same kinetic energy term that we had for the ideal gas, but that we now have this additional potential energy term. The summation here runs over the 0.5 multiplied by n minus 1 distinct pairs of atoms in our system, which is why the limits in the summations take the values that they do. Within the summation, you then have a function v that is a function of the vector rij that connects atom I to atom j. In fact, this function is often simply a function of the modulus of rij. In other words, it is often just a function of the distance between the two atoms. Furthermore, the fact that the energy depends on this distance makes a lot of sense, as we know that when atoms/molecules are close together, they will repel each other because the electron clouds overlap. When they get a little further away, they will then attract each other through weak intermolecular interactions, such as the multipolar interactions or the dipole-induced dipole interaction, the so-called London forces. And furthermore, we know that these attractive interactions will get weaker and weaker as the atoms get progressively further and further apart. In short, this Hamiltonian, which is a sum of a kinetic part and a potential part that depends on the distances between pairs of atoms, makes a great deal of sense. In order to make the equations that follow in the remainder of this video look slightly simpler, we are going to rewrite this Hamiltonian as shown here. To be clear, all we have done here is that we have replaced the sum over the n atoms in the first term with a sum over the 3n momentum coordinates. P1 in this case tells us the x component of the momentum of the first atom. P2 tells us the y component of the momentum of the first atom. P3 tells us the z component of the momentum of the first atom. The components of the momentum of the second atom are P4, P5 and P6, and so on. When we insert this Hamiltonian into our expression for the canonical partition function, we get the equation shown at the bottom of the slide. As discussed in the video on the ideal gas, the atoms can take any position within the volume V, and the momentum of each atom in each of the three Cartesian directions can take any value between -infinity and +infinity. The partition function is thus the 6n-dimensional integral shown here. Let me be totally clear on what this integral means. First of all, the ellipsis, the three dots, between the integral signs indicates that I should really have drawn 6n integral signs here, as I'm going to be performing 6n line integrals to calculate this object. There should thus be 3n integrals over momentum coordinates, and thus 3n dpj's, but a second ellipsis stands in for most of these. Similarly, there should be 3n integrals over position coordinates, and thus a third ellipsis is used to stand in for most of the 3n dxk's. On top of this, notice that I have not included limits in my integrals, and that I have thus wrote z as an indefinite integral. We saw in the video on the ideal gas, however, that the partition function z was a definite integral. To be totally clear, the partition function is a definite integral, so I should really have written the limits on the integrals. The limits for each of the position coordinates would have been between 0 and L, where L is the cube root of the volume V. The momentum coordinates, meanwhile, should run from -infinity to +infinity. I did not write these limits, however, because it is common practice in the statistical mechanics community, you will see this in many textbooks, not to write these limits in the integrals. Everyone in the field knows that the partition function is a definite integral, and thus we use an undecorated integral sign even though we are not strictly calculating an indefinite integral. Notice also in this expression that I have to divide by a factor of 8 to the 3n. As I discussed in my video on the ideal gas, this appears because whenever we do a double integral over a position and a momentum coordinate, we get a quantity in units of length times momentum out. We thus need to divide by a constant in units of length times momentum in order to ensure that z has no units, as ultimately we would calculate the logarithm of this quantity. As the 6n dimensional integral shown here is an integral over 3n position coordinates and 3n momentum coordinates, the final integral will be in units of length to the 3n multiplied by momentum to the 3n. We thus need to divide by 8 to the 3n to ensure that z is unitless. Right, so let's get on to the business of trying to solve this integral. The first thing we can do is exploit the trick that we have now used multiple times when looking at model systems. In short, we will rewrite the exponentials of any sums as products of exponential instead, and then separate out the variables in the integrals. The first simplification that we can perform using this trick will allow us to separate the momentum coordinates from the position coordinates, as shown here. We will thus rewrite this 6n dimensional integral as a product of two 3n dimensional integrals. We can go further than this with the exponential of sum to product of exponentials and separation of variables trick. The 3n dimensional integral over momentum coordinates can be separated into 3n separate one-dimensional integrals, as shown here. On top of this, all of these one-dimensional integrals are identical. So, although I have written this as a product here, I could have equally written this as a single integral raised to the power of 3n. We can also rewrite the exponential of the sum in the second term as a product. But at first glance, this does not look so helpful, as we cannot now separate the integration variables. It turns out, though, that this is helpful if we make a few far from obvious simplifications. The first of these will involve adding 1 and subtracting 1 from the expression in the product, which obviously does not change the value of the final integral at all. We will now introduce the symbol Fij and use this to represent e to the minus beta Vij minus 1. The e to the minus beta Vij that appears in this product, in the original equation, thus becomes 1 plus Fij, which we can expand as a series as shown here. Incidentally, there is an exercise in the comprehension exercises below that takes you through this process of proving that this series can be substituted for the product on the left-hand side of this equation. This series is very useful and is known as the cluster expansion. In practice, as well as the term with no sum and the term with two summations shown here, there will be terms with 3, 4, and all the way up to n summations within them, which is why the ellipsis appears in the equation that I have written. It's on the right-hand side. When Fij is small, however, as we would expect it to be for a gas, we can truncate this series and include only the first two terms in the expansion. As shown below, we can thus approximate the complicated 3n dimensional integral shown in the middle of this slide using the sum of the two integrals shown at the bottom of this slide. Let's now try to solve some of the integrals in this expression. Let's begin with the first integral after the brackets. The integrals over the position coordinates here are all variable separable. Furthermore, each of them will run from 0 to L, where L is the length of one of the sides of the box. This length is equal to the cube root of the volume, so this first multidimensional integral is thus simply L to the power of 3n, or the volume raised to the power of n. If we look at the integral in the product, we've also seen how to solve that one from the using tables in the video on the ideal gas. The integral here is the integrand here is just the Gaussian, and we know that the integral of the Gaussian over the domain running from minus infinity to plus infinity, we can look that up in tables. The value of the integral in this product is thus simply the square root of 2 pi m over beta. When we take the product of 3n of these integrals, we thus get that this first term is 2 pi m over beta, all raised to the power of 3 over 2, as shown here. The result that we have just arrived at is shown at the top of this slide. Notice that if you neglect the second integral here, the result we have is exactly the result we had for the ideal gas. Unsurprisingly then, everything concerned with the interactions between particles has been separated out into this second part of the equation. On the subject of the ideal gas, notice that we have thus far neglected the indistinguishability of the atoms, and have thus not resolved the Gibbs paradox. As we saw in the video on the ideal gas though, resolving this problem is simply a matter of multiplying the value we get for the partition function by a factor of 1 over n factorial, as shown here. Let's now turn back to the final integral we have to perform in order to get the partition function for this particular model system. This is the integral that incorporates everything to do with the interactions between the particles. We can make this problem look slightly more tractable if we reorder the integral and summation signs as shown here. Furthermore, it is perfectly acceptable to do this reordering as the integral of a sum of terms is the same as the sum of the integrals of those terms. Notice that the term inside the integral in the sum, the integrand, depends on only the positions of only 2 of the atoms. In other words, it depends on only 6 of the integration coordinates. We can thus separate out 3n minus 6 of the integration coordinates when we calculate this term. And we can rewrite each of these integrals in this sum as a product of a 6-dimensional integral over fij and 3n minus 6 line integrals that will run between 0 and L, and the integrand in these integrals will be equal to 1. Each of these integrals will give a value of L, and thus when these 3n minus 6 values of L are multiplied together, we will thus get a factor of v to the power of n minus 2, where n is the number of atoms. We can thus rewrite the 3n dimensional integral inside the sum here as a product of v to the power n minus 2 and a 6-dimensional integral, as shown on the right-hand side. On top of this, if we look at the sum, you will notice that the integrals in each of the half n minus 1 terms of the sum are identical, as the fij function is identical for all pairs of atoms, i.e. the potential interaction between each of the atoms is the same. The summation signs can thus be replaced by a factor of a half n minus 1, as shown here. Let's now turn back to the 6-dimensional integral. We can make further progress by employing coordinate transforms as described in my video on how we calculate the partition functions of molecules. In this case, for instance, we can integrate over the position of the centre of mass of the 2 atoms in the integral, and 3 coordinates, x12, y12, and z12, that describe the orientation of the vector connecting the 2 atoms. The position of the centre of mass will not affect the orientation of the vector connecting the 2 atoms, and thus it will not affect the value of f12, which you remember is a function of the vector connecting the 2 atoms. We can thus separate out the 3 integrals of the centre of mass coordinate. Once again, when we integrate these 3 integrals, we will get L's, and thus another factor of v. The integral thus becomes 1/2 n minus 1 v to the power n minus 1 multiplied by the 3-dimensional integral shown here. We represented the orientation of the vector connecting the 2 atoms using Cartesian coordinates x12, y12, and z12 here. But we could have used spherical polar coordinates r, theta, and phi instead. When we make this substitution, we find that the integral is given by the expression shown here. The limits of the integral now run from 0 to infinity for the r coordinate, from 0 to pi for the theta coordinate, and from minus pi to pi for the phi coordinate. Consequently, if we assume that f12 has no angular dependence, that is to say, if we assume that f12 only depends on r, the distance between the 2 atoms, then the integrals of phi and theta separate out and contribute a factor of 4 pi to the prefactor as shown here. Now, for any reasonably large n squared is going to be considerably larger than n, and we can thus approximate the integral we just arrived at as shown here. At the end of all this, we are thus just left with the line integral to perform, which appears much more tractable than the 6n dimensional integral that we started out with. Let's try and evaluate this integral now for a particular model potential. To do this, we are first going to need to work out how the energy of a pair of atoms changes as the atoms are moved closer together or further apart. As I alluded to at the start of this video, we know from subjects like electrostatics that when atoms are far apart, they do not interact strongly. We know, however, that as they are moved closer together, there is an attractive interaction between the atoms initially, as their constituent electron clouds configure themselves in a mutually favourable way. However, we also know that atoms have a finite size and that the shortest separations between them, the interactions between them, are repulsive. The simplest model that we can use to model this form of interaction is known as the hard spheres model. In this model, the potential is zero when the atoms are far apart. At a separation of A plus sigma, however, the potential changes discontinuously, and in order to incorporate the effect of the attractive interactions, the potential falls to a value of minus epsilon. The potential retains this value until the separation gets to a value of A. At this value, it changes discontinuously once more and shoots off to a value of plus infinity. This potential is known as the hard spheres model because this name provides a useful way of thinking about what the interaction potential does. Essentially, this model is assuming that each atom is a ball of radius A. These balls are hard and cannot overlap, which is why the potential shoots off to infinity at r equals A. Furthermore, these balls are sticky because of the attractive interactions between atoms. In the potential, the stickiness comes from the region where the potential falls to minus epsilon. Let's now calculate the integral from the previous slide for this particular potential. Obviously, when calculating this integral, it makes sense to divide the potential up into three separate parts. To divide the integral up into three separate parts. A part between 0 and a part between a and a plus sigma, and a part between a plus sigma and L as shown here. Furthermore, we also need to remember from earlier that the function f12 can be calculated from the potential as shown here. Consequently, when v is equal to plus infinity for values of r between 0 and a, f12 is equal to minus 1, as e to the minus infinity is 0. The first integral is thus simply the integral of minus r squared dr between 0 and a, which is simply a cubed over 3. The last of these three integrals is even easier. When v is equal to 0 for all values of r greater than a plus sigma, f12 is equal to 0, as e to the 0 is 1. The final integral is thus equal to 0. The last of these three integrals is similarly straightforward, but in many textbooks you will see that this integral is approximated, and I will thus take a moment to explain the approximation here. In essence, the exponential is replaced by its Maclaurin expansion, and this expansion is truncated at first order. The e to the beta epsilon is thus replaced by 1 plus beta times epsilon. The plus 1 and minus 1's cancel, and the beta epsilon can be taken outside of the integral, so that one is left with beta epsilon multiplied by the integral of r squared dr, as shown here. It is then straightforward to show that this integral is equal to the expression shown here. When we insert the values of these three integrals that we've just obtained into our expression for the canonical partition function, we get the equation shown at the top of this slide. To simplify this expression a bit, let's say that a cubed over 3 is equal to capital A, and that capital B is equal to 1/3 epsilon multiplied by a plus sigma all cubed minus a cubed, so that we can rewrite the integral on this page as a plus beta b. Our partition function in this expression thus becomes shown here. Notice that this can still be thought of as the sum of an ideal gas term and a correction term due to the interactions. but that now the interaction term is no longer a complicated-looking multiple integral. Instead, it has a relatively simple functional form that is a function of two parameters. We next recall that we can obtain the thermodynamic potential from the partition function using f equals minus kBt log z. Inserting the expression at the top of this slide into this relation gives us the following. Notice the product of an ideal gas term and the correction term in this logarithm. This screams to be written as the sum of two logarithms as shown here. Furthermore, when we do so, we see immediately that the first term is the free energy of the ideal gas, F ideal. The second term, meanwhile, can be approximated using the fact that the logarithm of 1 plus x is just equal to x, when x is small. We thus arrive at the following expression, and this is the free energy of the non-ideal gas, and is called the free energy of the van der Waals gas. We can take the expression that we just arrived at for the free energy and use it to calculate the equation of state. The first step in doing so is to remember that the free energy for an ideal gas, F ideal, can be written as some constant C, which will be equal to the free energy of the gas in some reference state, minus n kBt log V. This is useful as it ensures that we can rewrite the equation at the top of this slide as shown here. To get the equation of state, we need to take minus the first derivative of the free energy with respect to the volume. For the expression shown here, this partial derivative is as follows. Multiplying out the brackets in the expression gives us the following. If we then move the final term here on the right-hand side to the left-hand side and factorize what remains on the right-hand side, we arrive at this. Now, we could bring the two quotients on the right-hand side over a common denominator. Instead, though, we note that 1 over v plus an over 2v squared are the first two terms in the series expansion of 1 over v minus an over 2. This is a result that follows from the well-known result for the geometric series. We thus rewrite the term in brackets as 1 over v minus an over 2, so that when we multiply both sides by v minus an over 2, we get the following expression, which is the van der Waals equation of state. Here, once again, is the equation of state we have just arrived at. If you are anything like me, you are somewhat bemused by the derivation we have just performed, as it differs substantially from all of the other derivations that I presented thus far in this course. The problem that I had with this derivation when I first encountered it was that, especially towards the end, approximations were being made thick and fast and without any apparent logical rhyme or reason. For instance, the very last thing we did was to approximate a sum of two quotients that was on the right-hand side of the equation using a geometric series. Why did we not do the more usual and accurate algebra of bringing the two terms over a common denominator? The answer to this question is that we, or more accurately me, knew where we were trying to get to. We were trying to get this particular equation of state. This expression can be derived from a variety of different arguments, and often what we are doing when we use these statistical mechanical derivations is to show that the final equation of state that drops out for a particular model is consistent with the equations of state that have been derived by other means. We can thus make small approximations if by doing so we get closer to our final goal, namely this equation. After all, we know that the expression for the partition function that we wrote out at the start is unsolvable, and that every equation of state we will derive will thus be approximate. To make this more clear, let's think how we might have derived such an equation using a less sophisticated and more qualitative procedure. To do so, look at the terms in brackets. The first term is equal to P plus something, and we can think of it as an effective pressure. The second term, meanwhile, is V minus something, or an effective volume. We thus have effective pressure multiplied by effective volume is equal to nkBT, which is just the equation of state for the ideal gas, PV equals nkBT, with the pressure and volume replaced by an effective pressure and an effective volume. When we look at the equation in this way, the meanings of the parameters A and B become clearer. The A term is related to the volume of a single atom. By including the AN over 2 term, we thus ensure that the volume that each of the atoms can move about in is smaller than the total volume of the space. Each atom moves around in a reduced space because the two atoms cannot interact. The B over 2 multiplied by N over V all squared terms is there to mimic the effect of the attractive and repulsive forces that the atoms have and the effect that these have on the pressure. These additional forces will either increase or decrease the pressure experienced by the walls of the container. The van der Waals equation of state was initially derived using considerations similar to these. This is why the derivations in the previous slide perhaps feel peculiar. We knew where we were trying to get to, and we were thus making approximations in order to ensure that we got there. There is a lot of mathematics in this video. Let's thus finish by summarizing the most important aspects. If we have a system of interacting particles, we can describe it using a Hamiltonian, something like the equation at the top of this slide. When this is inserted into the expression for the canonical partition function and a few obvious manipulations are performed, we arrive at an expression for the partition function that looks something like this. It is important to note at this stage that the 3n-dimensional configurational integral in this expression cannot be solved exactly. Thus, whenever it comes to solving an integral, like this one, an approximation is required. The approximation that we've employed in this video is known as the cluster expansion. In essence, we recognize that the product here can be written as a series with n terms. When this series is inserted back into the integral becomes a sum of integrals. The first of these integrals consists of one-body integrals, the second contains all two-atom integrals, the third will consist of three-body integrals, and the jth term in the series will consist of j-atom integrals. That is to say, in calculating the j-body integral, we will have to integrate over the coordinates of j different atoms. What makes this series expansion useful is that the value of the n plus 1 body integral is usually much smaller than the value of the n body integral. Consequently, we can truncate the series and only evaluate integrals involving small numbers of atoms. Furthermore, it is very common to truncate these series after the second term and thus only consider the one-body and two-body terms in the series. In the video, we showed how this works out when we consider the half sphere potentials, and thus we got to one way of deriving the van der Waals equation of state. The cluster expansion approximation can be and is used to do more than just this, however. Furthermore, the fact that the interaction potential can be written as a sum of one-body terms, two-body terms, and three-body terms, and so on, and the fact that it is reasonable to truncate this series at two-body or three-body interactions, underpins many of the techniques that are used in the field of atomic simulation, which is the topic that we are going to study next. For now, though, have a go at the problems and try and consolidate what you have learned from this video. Thank you for your attention.